Welcome to The Explainer. Today, we're talking about how to protect the most fragile thing in the universe, a single piece of quantum information. This is the story of the Shor code, a truly brilliant defense system that basically made the dream of quantum computing a real possibility.
Right. So this is the fundamental, kind of mind-bending challenge at the heart of building a quantum computer. See, the very act of looking at quantum information, it destroys it. So how in the world can you check it for errors? It's like trying to find a typo in a letter that just bursts into flames the moment you open it.
So, here's our game plan. We're going to break down why qubits are so fragile, then introduce the code that first came to the rescue. We'll see how its two-layered shield works, and then understand how it created a universal rulebook for building a quantum future. Let's get right into it.
Okay, first things first, let's meet the villain of our story, quantum fragility. To really get why the solution is so clever, you have to understand just how delicate these things are.
Think about it this way. The bits in your laptop are like light switches, right? They're either on or off. Simple. But a qubit, it's more like a perfectly balanced spinning coin, holding this delicate mix of possibilities. The tiniest vibration, a stray magnetic field, even just a little bit of heat can be enough to knock it over and completely wreck your calculation.
And here's the kicker. We can't just guard against one type of mistake, like a bit flipping from a 0 to a 1. Nope, we need a system that can handle any possible error, even ones we can't predict. It's like designing a bodyguard that has to be ready for a bullet, a ninja, and a random meteor strike all at the same time.
And that brings us to the solution. Our hero, if you will. It was a massive breakthrough from mathematician Peter Shor way back in 1995.
And this was the moment that really changed everything. Before this, people weren't sure if building a useful quantum computer was even possible because of that fragility problem. Shor's code was the first real proof of concept that said, yes, it can be done.
But the way it actually pulls this off is, well, it's pretty surprising. It all comes down to redundancy, but on a scale that just seems kind of wild.
So to protect just one of those precious, fragile pieces of quantum data,
You need 9 physical qubits to act as its bodyguard. That's right, a 9-for-1 trade. It sounds crazy inefficient, I know, but it turns out that in this crowd, you find security.
All right, so how does this team of 9 qubits create such an amazing shield? The genius here is in its two-layered approach. It's built to fight two totally different kinds of quantum errors simultaneously.
Think of it like this. A bit flip. That's pretty easy to picture. It's just a coin flipping from heads to tails. But a phase flip, that's a purely quantum kind of error. It's like the way the coin is spinning gets messed up. The Shor code has a defense for both. And here's how those two layers work. The 9 qubits are split into 3 little squads. The first layer of defense works inside each of those squads, using a simple majority vote to fix any bit flips. Then, the second layer looks at the relationship between the squads to catch those much trickier phase flips. It's a complete defense system.
And this is the real magic. Remember that burning letter problem? You can't just look at a qubit to check it. So instead, the code uses helper qubits to ask indirect questions. It's kind of like a teacher asking a group of students, hey, did you all get the same answer? Without actually asking what the answer is. That response, the syndrome, tells you if there's an error and where it is, without ever revealing the data itself.
Now, the Shor code wasn't just some one-off trick. Its success actually uncovered a much deeper, more elegant way to think about quantum error correction in general.
This whole structure is called the stabilizer formalism. And honestly, the best way to think of it is as a rule book for your protected qubit. If the qubit is perfect, error-free, it obeys every single rule in the book. But the second an error happens, it breaks one of the rules. And that broken rule acts like an alarm bell, telling us exactly what went wrong.
Now you do not need to understand the math here, just the big idea. These rules are the stabilizers you see here. The Z rules are basically asking, is everyone in Squad 1 okay? How about Squad 2? They're checking for bit flips inside each little group. The X rules at the bottom, they ask bigger picture questions across all the squads. That's how they detect the phase flips. By just seeing which rules are broken, we can diagnose the exact error and apply the perfect fix.
So what's the big takeaway here? Why does this code, which is nearly 30 years old, still matter so much today in the massive global race to build a quantum computer? It's because this was so much more than a clever trick. The core principles of the Shor code, using redundancy for strength, measuring errors indirectly, that whole stabilizer rulebook, that's the absolute bedrock of all modern quantum error correction. It's the blueprint for building a machine that can actually tolerate errors and do something useful.
And that leads us right to today. This isn't just theory on a blackboard anymore. It's a massive, real-world engineering challenge. Labs and companies all over the world are in this race, not just to build these codes, but to make them way, way more efficient.
And that leaves us with the billion-dollar question. The Shor code proved that protection is possible, which is amazing. But is a 9-to-1 overhead really sustainable when you start talking about a computer with 1,000,000 qubits? Probably not. We know the bodyguard works. Now, the hunt is on to make it leaner, faster, and a whole lot stronger.